contribute to the neutral current breakup of the deuterium. This is a fantastic idea. Of course, by the time the snow detector actually got built, unfortunately Chen died but otherwise he would certainly have received the Nobel Prize. But of course the other team members did a fantastic job, and in 2015, the seminal paper was in 2002 when the snow published the results. This is a little after 4 years after the Kamioka result, which had also evidence for neutrino oscillations, but snow had it about 4 years later. But they basically solved the solar neutrino problem because they found a signal which is sensitive to all kinds of neutrinos, a kind of sum of the flux of all neutrinos, and in the same detector, a signal from the electron type of neutrino. So in the same detector, you have a ratio which is of the order of 1/3, and they completely cracked the problem. Okay, so what is the explanation for both the atmospheric neutrinos anomaly as well as, I haven't said anything about the atmospheric neutrino anomaly, but let me just say in words that the atmospheric neutrino anomaly was that Kamioka found that downward going neutrinos, they found 2-to-1 ratio for the muon type to the electron type, and the upward going neutrinos, those that pass through almost the diameter of the Earth, they are in the ratio 1:1. So that was the atmospheric neutrino problem. And both these problems were solved in one stroke by invoking neutrino oscillations. And this is, I think, a very nice quote from Bacall, that solar neutrinos have a multiple personality disorder. They are created as electron neutrinos in the sun, but transform on the way to the Earth due to a quantum mechanical process. So we know this can happen, and this is a very nice way of putting it to the public. This is a case of, I think, a very good outreach. So in '69, Monte Carlo proposed neutrino oscillations, but matter effects were taken into account by Wolfenstein, and then Mikhail Smirnov built on that. And so this is known as the MSW effect, where you can have resonant transformations of the electron type of neutrino to the muon or the tau type of neutrino. Okay. So if you start out with, let's say, just for example, a muon type, then as it propagates, it becomes a mixture of these three mass eigenstates. Then comes back at some point, and that's why it's got an oscillation, comes back to the muon type and so on. And this continues as it propagates in space. Okay, so just again, maybe I should try. So this is a simple case of neutrino oscillations to show, which has only two flavors mixing, and this can be very easily shown. The main thing to see here is that the survival probability of a neutrino of a particular flavor is 1 minus a mixing angle, a sine squared mixing angle squared, and sine squared is something here which depends on delta m squared, difference in squares of two masses, of the two mass eigenstates involved, and L by E. Now, it is clear from here that if theta is 0, then there is no oscillation. Similarly, if delta m squared is 0, again, then there is no oscillation. So if you see evidence for oscillation, it means that delta m squared is non-zero, and also means that theta is not 0. So there are essentially two kinds of experiments in neutrino physics which look at these oscillation aspects. That's the so-called disappearance experiment, which means you start out with a muon, let's say a flavor of neutrino, and you look for the muon type of neutrino. So you see a dip, and then maybe a rise and so on. But then there are also appearance experiments, which are in principle more sensitive, especially when there's small mixing, where you start out with a certain flavor of neutrino and then you come out with a different flavor. So you look at the different flavored electron. Okay, now real life, we know that there are three flavors, so actually there's a 3x3 unitary matrix. So I will not go through this except to say that there are two delta m squareds, and of course there's an absolute scale of the mass, which we don't know how much it is. It's certainly we know from absolute mass measurement that is of the order of less than 1 eV, but we don't know what is the exact value. And then there are three mixing angles, analogous to the, when you rotate a vector. I mean, when you rotate a coordinate frame, then the vector has to be represented in these two representations. That there are three angles that come out. They are essentially analogous to those Euler angles. And these, it turns out, are very large, unlike some of the mixings that you observe in the quark sector. For instance, theta 2,3 is close to maximum, because you saw that 2 theta enters, so that's close to 90 degrees, so that's the maximum mixing. But the most interesting result, so anyway, there are many, many experiments which have pinned down these values, some values even more accurately than other values, like for instance, this is a small mixing angle, but this has been pinned down in a reactor anti-neutrino experiment, and is probably the most precise value for any of these mixing parameters known. The interesting thing is that there is evidence at the 3 sigma level from the T2K collaboration. This is the Japanese collaboration. They sent neutrinos from JPAR to the Kamiokande, super Kamiokande detector, and they have found that there is CP violation in this. So neutrinos and antineutrinos behave differently. The oscillation phenomena that is a little different. And this mixing angle that is involved, this is actually the phase angle, I should say. This is almost close to the maximum in their analysis. There is some disagreement between other experiments in the US, but hopefully time will make this things will form out, I guess. Hyperkamika, of course, will be a much higher statistics experiment, and that will probably fix this, nail down the delta CP, as other experiments as well, which might come up at that time. Okay, so there are many experiments, as I said. This is probably not the time to discuss all of that. I'll just say that there are many detectors coming up for reactor and solar neutrinos, and the biggest one is the one coming in China. This is called Juno detector, and they actually want to measure mass ordering using reactor antineutrinos. This is a great challenge because the detector has to have a very high resolution of the order of sigma E by E of the order of about 3% at 1 MeV, but the collaboration thinks that they can do it, and if they can, then they will solve this mass ordering problem by measuring the reactor antineutrinos. Of course, this being such a huge detector, it will also have other capabilities. It can measure geoneutrinos, it can measure other things, but dark matter decay, that the slew of things that can. Then there is another detector, big scintillation detector, which is coming up in Sudbury. This is a follow-up of the D2O detector that they had, but this time it's a liquid scintillator, and the goal is that they will put tellurium of the order of up to 0.5% in this 1 kiloton liquid scintillator, and then measure the neutrino-less double beta decay, which will tell us whether the neutrino is its own antiparticle or not, whether it's a Majorana particle or a Dirac particle. In the area of solar neutrinos, I tend to go back. Okay. In the area of solar neutrinos, there are some open problems, like for instance, the survival probability of the electron type of neutrino as a function of the energy of the neutrino. The Mikhail-Smirnov-Wolfenstein paradigm gives you a certain dependence, and I will show a graph a little later. And there are non-standard interaction theories which go beyond the standard model, which show a very different dependence. But there is probably again a slew of such other theories, okay, which give sometimes a very different dependence as compared to the LSW paradigm calculation. Okay. There is also this effect that as the neutrinos pass through the core of the Earth, and if the detector happens to be at the night, then the solar neutrinos are going through the Earth, and then they will undergo a small matter effect. The density, of course, of the core of the Earth is not that high; it's about 13 grams per cc. But nevertheless, it should show an effect of the order of 10%. But the higher energy sector, in fact, this is expected to be a 10% effect. That means the sun should shine brighter at night in the neutrinos than in the day for the high energy. For the low energy neutrinos, it's the other way around. It is weaker. Again, by a few 5-10%. In fact, not even 5%, it would be slightly smaller because it's an energy dependent effect. Okay. So we are thinking of still, I should say that it's very early days, but we have started thinking about the possibility of a deuterated liquid scintillator for precision solar and perhaps even supernova neutrinos if you're lucky. The idea is that the scintillator signal is about 50 times the Cherenkov of photon signal. And so you can hope to get of the order of 400 or maybe 200 keV versus the 5 MeV threshold that exists in all the water jet detectors. Deuterium, since it contains neutrons and protons, allows you to study charge current interactions of neutrinos as well as antineutrinos. Okay? Of course, there are thresholds involved, so if you go to very low energy neutrinos, you may not be able to see both neutrinos and antineutrinos, but we had proposed this first in the context of supernova neutrinos, but of course this can also be used for solar neutrinos. That's what we are working on right now. So why a deuterated liquid scintillator in India? The strength is that we are the largest producers of heavy water in the world. So we have the largest probably store of potentially pure deuterium. If we can make a liquid scintillator, then that would be fantastic. And so we have started some R&D on this. Of course, there are some administrative things that have happened. And the first results from just the beginning, making a linear alkyl benzene-based liquid scintillator, this looks promising. We have also taken the benzene, so C6D6, deuterated benzene, and put some pop and things like that, which would make things scintillate, and that seems to be quite encouraging, but there's a long way to go. And we have also looked at what are the possibilities of deuterating a liquid scintillator. So this is a long chain. It may be difficult or perhaps even impossible to do it for this. This, by the way, was used in the Diabe experiment and by many other experiments. In fact, even the 20 kiloton detector of the Chinese, the Juno, is going to use linear benzene. So that may be difficult. If so, then it might be somewhat easier to do it for xylene because the chain that connects to the benzene is smaller. And finally, even if that bit is difficult, there is also the option that you can go somewhere between a scintillator and a Cherenkov detector, which means you have a water-soluble liquid scintillator, so which is predominantly D2O, 95% let's say, and then you have a hydrogen-based liquid scintillator, which we all, we hope we will be able to do that. And the idea that the first step would be to make a one-ton prototype hydrogen-based liquid scintillator and deuterated liquid scintillator and deploy it at a nuclear power plant and then characterize it. So this is a picture of potentially what this could be, a 1 ton prototype detector. Okay, the estimated, so the first paper that we wrote on this is started off with looking at the possibility of a 1 kiloton deuterated liquid scintillator for a typical supernova at 10 kiloparsec, and this is the reference. So the number of events is of the order of a few hundred, neutral current as well as charge current. But obviously nobody is going to fund you for detecting an event which occurs once in 30 or 40 years. And so we immediately started looking for this in the solar neutrino sector because these neutrinos are always there. And for instance, one of the things which we estimated is that in this survival probability of the electron type of neutrino from the sun versus energy, there are data points from Orexino and so on, and then there are also points from SNO and Super Kamiokande. But there is a gap between about, say, 7 MeV to about less than an MeV. So there are various kinds of non-standard models which predict something which is different from the Mikhail spin-off. So it would be interesting to have this measurement at energies which can be done with a deuterated liquid scintillator. Okay, this is a slightly different line. At one point, we had become a little desperate of how to find a suitable site for the INO. We didn't, somehow we didn't get that much support from the local government. So we, in response to a question, we set up an experiment for the INO graduate training program. And there were 3 students involved in that and 1 PhD student of the INO GDP. And to my surprise, we set up an experiment. I had expected something like 2 nines or at most 99.5% efficiency. The idea is that you put a veto detector at shallow depth, and can you do the neutrino experiment? It's a crazy question maybe to ask. But if you have to answer this, you have to do some experimentation, right? So this is the first small step that we did. We built a small detector and then found to our surprise, at least to my surprise, that this was a veto efficiency of 99.98%. Some error bar. So this motivated a proposal to build such a detector around the mini ACL, which has now been running for about 4 or 5 years at Madurai. That's a 4 meter by 4 meter by 1.2 meter magnetic device that is basically counting cosmic muons, but more it is helping us understand some of the problems that come up when you want to build up a larger detector, which would be the engineering module, which is about 10 times bigger than this. Okay. so that involves extruded plastic scintillator, and also you have to have WLS fiber, silicon PMs. So this is slightly early, this is slightly dated, maybe about 3-4 months back now. Of course, they have very nice panels which are ready to put around the magnet, and this is what we hope to do at Madurai. And you might ask, okay, now suppose we get a site which is deep, then what do you do with this? Okay, so possible use of this. Of course, it can be used, but this, if you have a nice site, who would want to do this? Suitably configured, it can also be used, and we have a couple of papers as part of the thesis of Nitali, one of our INO graduate training program students, PhD students, that you can look for exotic things. You can put these things on the walls of the cavern, and for instance, you could do in a year what KGF accumulated as anomalous events in something like 15 years or so. Okay, so you can look at, also you can look for monopoles, for instance, and so on. Additionally, this could also be used for small size detectors to substantially reduce the background due to cosmic muons. For instance, in astrophysical cross-section, gamma energy cross-sections are of the order of picobarn or fractions of picobarn. So there it is important to reduce the muon-induced background, and that this might help. Still, you would require a shallow depth, or you require a recoil mass separator or something like that. But in any case, this would help reduce the background. 5 minutes, okay. I'm almost a few slides. So the next step is that we want to build an engineering ICAL module, and we had a place in Madurai to do that, but somehow it just took too long to get the permissions, because as I said, the government was not keen on the main project, and they dragged their feet on giving us permission. We did get it about a year or so back, but now the question is that if it may be a little risky to do anything here, because so we are looking for potential sites for housing this. Yeah, I'm sure we will find one in a month or so from now. And the idea is that we build a detector which is roughly 10 times bigger than that mini ICAL. We call it mini ICAL at Madurai. So it will have, it will be a 8 meter by 8 meter, 320 RPCs, and of course the materials for that are there in the at least the ones from the magnet. Low carbon steel is to be sent now for machining. The order is finalized, I think. Copper coils are already ready at BRC. Glass RPCs we have ordered 20 from another vendor, and we hope that that vendor will deliver, and we might be able to refurbish the ones which we got from Sankubai near Chennai. Then the Anusparsh acid, which is made to amplify the signals from the RPC, and that's part of the front end board. That fabrication is going on in BRC again, and this has to be finalized, of course. So this is my last slide. So what can INO do and what can ICAL do? So this will be prepared by Amol. So of course, at the outermost you find that large state-of-art experiments in India. This is good for developing expertise, for making leaders through experiments done in the country, and also it's a great thing for education and research opportunities for students as well as of course their faculty. Then this low radiation lab is also good for other experiments like nuclear astrophysics, or even nuclear physics with particle physics connotations, geology, and so on. Then this is something that we would like to say, because this is the era now of multi-messenger astronomy. You have the gravitational wave detectors, you have detectors in the circling around the Earth, and at way out places on the globe. And so this could keep monitoring neutrinos for a long time to come. And with the idea that since you have a magnetized detector, you will separate neutrinos from anti-neutrinos of the muon type. You will also, of course, search for physics beyond the standard model, get some handle in a very different kind of detector for the mixing parameters, look at non-standard interaction, etc. Possibly even throw some light or some make some dent in Earth's tomography, because this is the only detector that can look at all neutrinos and separate out the nu mu and the nu mu bar, and look at what happens to neutrinos passing through the Earth, the core of the Earth, for instance. And of course, finally, we could use the matter effect. But all this, of course, has to happen after we find a site, which we are in the process of doing right now. So let me end by thanking you all for your attention.
Thank you, Vivek. So it is now open for comment, question. Yeah.
So thank you for this very nice overview, broad view of the various areas of geophysics. My question is, what is currently the status of knowledge about the hierarchy, which is of course very relevant for all beta decay experiments?
Yeah, okay. So
what is the prospect for the next 3 to 5 years?
Okay, so I think the prospect for the next 3 to 5 years is to actually build the detector. We are not going anywhere.
But to measure the hierarchy, there are different...
To measure the hierarchy, it would take a minimum of 6 years of the detector running together with other experiments. If you do it independently, of course, that's something like 9 years.
But the question is in the next, just from starting from now, next 5 years.
But what is known today? I think today we are already at the 2.5 sigma indication for normal hierarchy. Is that correct?
It's about 3 sigma in about 9 years time or so.
No, but today.
Of the detector, all 3 detectors running. Yeah.
So if you know what is known today.
Yeah. Oh, yeah.
Already today we have indication that the normal hierarchy is more likely.
Yeah.
So I want to know what is the evidence for the normal hierarchy? How many sigma is it today?
I think that is, right now it is like, I think 2 or a little more than 2 sigma, taking all the data that is around.
Only 2 sigma.
Yeah, but see, if this Chinese experiment gets going, as they say, maybe in the next 3 years or so, they will have the hierarchy to at least 3 sigma.
Okay.
So, but the challenge there is that for a 20 kiloton detector at 1 MeV, you want 3% resolution. So it's not that, if you get 3.5, you will take maybe instead of 3 years, 4 years. It's not that. Then you just will not be able to do it. Okay, so that's a challenge. But of course, they are quite very competent people in that, and it's possible that they will actually get that kind of resolution that they have in mind.
I think the real answer will come when you come into existence, and that they will do within something like 6 sigma significance, the mass hierarchy. I think that is the experiment, that time scale. So time scale is from now on is roughly around 10 years.
For due.
Yes, I mean for 6,
That's
that many sigma, significant result of the mass hierarchy
That's
at that time.
That's right.
Suvik.
So, idea of building a beyond veto is obviously a good solution if you can't go underground.
Yeah.
And you said you would achieve a veto efficiency of 10 to the minus 2%, 10 to the minus 4.
Yeah. The veto, leakage of 10 to the minus 4.
Yeah, so that's very impressive, but the fact is that the atmospheric beyond background, as you know, is a million times higher than the atmospheric neutrino flux. We measure both in ice cubes, so we know. So even with 10 to the minus 4 suppression, you still have a...
So I didn't give the caveat to that. Obviously, it is not possible to do such an experiment overground. It's quite clear. So you have to go underground, but you need not find a site which is, at least 1 kilometer deep. And I said this was in a time of desperation that we thought about this. So we estimated that if you are at 100 meters below the surface, the muon flux decreases by a factor of 100. Then this 10 to the 4 helps, and then you are at roughly the same level as a 1 kilometer underground laboratory. Okay, and we did a simulation, so I didn't go show the reference there, but we have a simulation of that, and things are under control. Indeed, you can measure.
So are there suitable sites